Capstone Project, you'll answer a research question for yourself. Do CNNs rely on low spatial frequencies to classify images? You will construct a CNN and train it on the Fashion MNIST data set. You only train it once, and then you evaluate it multiple times under different frequency ablation conditions to draw this conclusion. As always, there is a project notebook and a solution notebook. The links to these notebooks will be provided in the description of this video. Let's look at the project notebook. If you haven't watched the video on lesson 10, which discusses how to use PyTorch to code all of this, I urge you to do so before you embark on this project. In this video, I'm only going to go over the to-do cells. In the first couple of cells, we load the Fashion MNIST dataset, and we create our training and test data loaders. Then we get to our first to-do cell. Here, you define your CNN. First, you create a convolutional block that should be composed of 2 convolutional layers, 2 ReLU layers, and 2 max pooling layers. That's all you need in order to classify the relatively simple images in the Fashion MNIST dataset. Of course, these layers should be interleaved, and the block should increase the number of channels from 1, since these are black and white images, to 64 by the end of this block. And it should also reduce the image size from 28 by 28 to 7 by 7 using the 2 max pooling layers. Then you move on to your fully connected block, which is really a feed-forward network that first flattens the output of the convolutional block and then applies 2 linear layers, and these are separated by a single ReLU layer. This block should reduce the vector size from 64 by 7 by 7, which is the flattened output of the convolutional layer, to 10, and the reason it needs to reduce it to 10 is because we have 10 classes into which we want to classify the images. It will use the feature it receives from the convolutional block to produce logits for the 10 classes. Once you have done this, then you can simply define your forward function, which passes the input X through the convolutional block, and that extracts the features. Then it feeds those features to the fully connected block and returns the output. And the output are the logits that will later be supplied to the softmax to create a probability distribution. Here I have instantiated your model for you and put it on the GPU. In your second to-do cell, you will select a loss function and an optimizer. Start out with a learning rate of 0.001, and you can modify it later if you want. There's a test cell for that. And then you define your training function, your training loop. First you have to, of course, move your inputs and labels to the correct device, which is the GPU. You apply the instantiated model to the inputs, and you calculate the loss using the given loss function, whatever that is, whatever you have specified. You then propagate the loss backward to compute gradients, and in PyTorch this is just one short line of code. And then you use the optimizer to apply those gradients and update the weights, another short line of code, and then you reset the optimizer so that it can apply itself to future batches. There's a test cell for this. I have defined the test function for you, and that's that for creating the CNN. Then you move on to the frequency ablation experiments. Fourth to-do cell, you will construct your masks. Each mask takes a particular 2-dimensional spatial frequency given by the radius on the magnitude spectrum for that image, and decides whether to pass that frequency or not. It does so by comparing that frequency against a cutoff, a threshold. You define the low pass and the high pass masks. For the band stop mask, you're given two cutoff frequencies, and you need to pass only the frequencies that are either lower than the lower cutoff or higher than the higher cutoff, and you stop any frequency that's between the low and high cutoff. Finally, in your fifth to-do cell, you use the Fourier transforms to actually knock out certain frequencies. You use PyTorch's fast Fourier transform, which allows you to take in a batch of images and apply the mask to them. As with any Fourier transform, first you apply the transform and then you have to shift the DC component to the center. So there are two lines of code here. And furthermore, with PyTorch's fast Fourier transform, you have the luxury of being able to specify the dimensions, and you want to make sure that the Fourier transform is only applied to the second and third dimension, which are the height and width of the image. Once you have your shifted transform, then you apply the mask that you're given, whatever that mask is, to it by simply multiplying the mask by the shifted transform. And finally, you do the inverse shift and the inverse fast Fourier transform again over the last two dimensions and return the output. That's it. And then the rest of the code will print out or display a CNN frequency reliance curve for you, which hopefully will look like what we saw in lesson 9.